and I'll be moderating today's webinar. Before we start, I'd like to run through just a few housekeeping items with you. First, while you won't be able to speak directly to the presenters, if you have questions as we go through the presentation, please feel free to submit them through the questions section of the GoToWebinar tab that you see there on your screen, and we'll get those answered for you at the end of the presentation. Also, the webinar will be recorded today, and a link will be sent to everyone via email tomorrow, so keep an eye out for that. And I'd like to start off by introducing you to MinTech, just so you have a better idea of who you're hearing from today. We are a 100% turnkey material handling solutions company. We were founded in 1998. We've got a team of engineers, chemists, and application specialists with hundreds of years of combined experience solving all kinds of material handling issues. Whether it's surface or process dust control, like what we're going to be discussing today, erosion control, fire prevention, freeze conditioning, conveyor and chute maintenance, or even industrial cleaning, we've got all that stuff covered. We have a unique three-pronged approach to resolving our customers' issues, and that's what really sets us apart in the industry, and you'll hear just a little bit about that at the very end of the presentation today. For a more detailed overview of our services, you can download our MinTech flyers. There's 3 of them. You can find them in the handout section right there on your screen in the GoToWebinar application. And now I'd like to introduce today's speakers. First, we have Chris Raymond. Chris is our technical director here at MinTech. He's been with the company since 2012, and he's in charge of our product research, design, and customization efforts. He spends a lot of time out in the field with our customers and MinTech engineers, helping tailor solutions for different facilities, different specific needs. He's also our resident coal expert and self-proclaimed science nerd. He can talk science all day, every day to anybody, and his wife can definitely attest to that. Our second speaker is Wes Gary. Wes is our Chief Technical Officer, and he's been with the company since 2000. He oversees our R&D process to ensure we produce a consistent pipeline of unique and effective solutions for our customers. He's got a wealth of experience in material handling industry and has worked with many different industrial facilities, from coal-fired power to mines to quarries to fertilizer manufacturers and lots more. He works with them to resolve dust-related issues, including compliance, safety, always keep an eye on budgetary concerns. Wes is an avid runner, and he's also an Eagle Scout. And with that, I will go ahead and turn it over to Wes and Chris.
Thank you for that introduction, Kendra, and thank you to everyone who is joining us today. Our plan is to provide a straightforward, unbiased comparison of dust collection and dust suppression. Our goal is that through the course of this webinar, you're going to learn something that's going to help you choose the best dust control solution for your specific needs, whether it be collection or suppression or a combination of the two. Our hope is that we earn your trust and gain your confidence in MinTech, so that perhaps one day you'll invite us to help you solve some of your dust control and material handling problems. We're going to start our presentation today with a brief overview of current dust regulations. Then we'll review the major challenges related to dust control. Then we'll highlight the main advantages and disadvantages of dust collection versus dust suppression. Our focus is going to be on safety and efficacy. And we'll close with a comparison of the total cost of ownership of dust collection versus dust suppression. So without further ado, I'll turn this over to Chris Raymond to get us started.
Thanks, Wes, and good afternoon to everybody who's with us. First, what is dust? Dust is solid particulate matter, and it can range in size from about 1 micron in diameter to greater than 1,000 microns in diameter. The yellow area highlighted in this chart represents the size range of dust relative to other materials like smoke, soot, bacteria, and pollen, to name a few. So dust represents a pretty wide range of particle diameters. And dust is more than just a nuisance. There are 4 major reasons why it's important to control dust. First, dust causes adverse health effects. Respirable dust particles are those in size of 1 micron to 10 microns in size. Particles this size are small enough to enter the narrow passageways of the lung, but are too large to excrete from those passageways. Dust-related diseases include black lung disease, silicosis, and COPD, to name a few. The second reason to control dust is that dust causes environmental damage. Dust damages plants and crops by blocking photosynthesis of the leaf surfaces. Dust pollutes waterways by raising the turbidity level and creates a toxic environment for marine organisms. Dust can also acidify soils and make changes to nutrient cycles. The third reason to control dust is dust causes excessive maintenance to machines. Dust clogs air filters, reduces equipment efficiency, and can cause equipment failures. The fourth major reason to control dust is that some types of dust can be explosive. Now, not all types of dust are combustible dust. For example, clay, gypsum, and limestone are not going to catch fire. But many dusts are combustible and can explode under the right conditions. Given these four major dust hazards, it's no wonder there's so many regulations about dust and why several government agencies are putting more and more focus on controlling dust. Let's talk about the three agencies involved with dust regulations and their jurisdictions. OSHA has jurisdictions on dust levels in workplace environments, mainly within property lines and boundaries. MSHA has jurisdictions on dust levels in all mines, including coal, metal, and non-metal mining operations. And the EPA has jurisdiction pretty much everywhere else. Basically, any dust leaving properties and crossing into the public domain or into a neighboring property. The regulatory limits imposed by each agency are similar, but do vary slightly. OSHA's respirable dust limit is actually 2.0 milligrams per cubic meter, averaged over 8-hour periods. OSHA also requires combustible dust accumulation to be less than 1/32 of an inch. MSHA's respirable dust standards are 1.5 milligrams per cubic meter, also averaged over 8 hours. And the EPA emission limit is 0.15 milligrams per cubic meter over a 24-hour period of time. And the opacity limit set by the EPA must remain 10% or less in a dust cloud.
So let's talk about the challenges of dust that are facing industry today. The biggest challenge and the most costly challenge is the D word. We're talking about downtime. Downtime can be attributed to scheduled cleaning and dust removal tasks, and downtime can also be attributed to unscheduled tasks caused by premature equipment wear. Many industrial processes such as grinding, shredding, crushing, and sanding generate dust that build up on floors, pipes, beams, ledges, and equipment. According to the ISSA, the cost to remove dust from a building can exceed $600 per pound. The cost of unscheduled downtime is a little bit more difficult to quantify because the timeline is longer and the factors involved are more subtle. Here's one way that dust causes unscheduled downtime. Dust can infiltrate the small openings in equipment, finding its way to bearings, gears, and other moving parts, where it can embed, dent, and scar the inner workings of machinery. While lubrication filters and air filters are designed to remove dust to protect equipment, studies performed by WearCheck International demonstrate that even the best seals and filters can't keep all of the dust out of the machine. Eventually, the dust wins, and the equipment fails, creating unscheduled downtime. Dust-caused equipment failure is estimated to cost American industry more than $2 billion per year in unscheduled downtime. Chris mentioned combustible dust a few minutes ago, and I'd like to revisit that because it's a growing challenge to many industries. While dust in general can have a profound effect on a company's bottom line, combustible dust can wipe out a company entirely, destroying entire facilities and killing employees. Between 1981 and 2005, there were 281 fires and explosions caused by combustible dust. 119 people died, 718 were injured. The property damage of those events is estimated to exceed $500 million. Add to that $25 million in fines, and it's clear that combustible dust deserves more attention. Here are the details of just 2 of those incidents. 5 workers were killed at an iron ore dust explosion in Tennessee at Haganese Corporation. At the time, dust collectors were down for maintenance, and no one was performing routine housekeeping practices to remove combustible dust from beams, ledges, or equipment. 14 workers were killed because of a sugar dust explosion at Imperial Sugar Refinery in Georgia. The plant had a spillage problem when a chute was clogged, causing dust to be lofted into the air. Large amounts of airborne sugar dust reached explosive concentrations and were ignited, likely by an overheated bearing, which was most likely overheating due to, you guessed it, dust intrusion into the bearing.
This is a poster produced by OSHA listing many common combustible dusts. As you can see, there's a wide variety of substances affecting dozens of different industries. You have food substances, which include sugar, starches, flour, grain, tobacco, and some grasses. Non-food substances include certain plastics, wood, paper, rubber, coal, and certain metals. The 3-pronged approach to controlling combustible dust is to contain, capture, and clean it up. 2 other challenges related to dust are reduction in quality and a reduction in the performance of the material. Dust collection or dust suppression can be used to prevent cross-contamination between 2 different process lines. Dust collection can be used to refine and separate dust generated by processes. Let's consider kaolinite, for example. If this product becomes contaminated, it could drastically alter the performance of the material. Dust suppression is used to prevent airborne cross-contamination, while dust collection is then used to screen out fines that aren't within the size parameters required. Dust has also been associated with performance loss. Let's consider coal as an example. Dust emissions from a coal pile can contribute to 0.5% lost energy or lost BTUs. Now, that might not seem like a lot, but when you consider the billions of dollars spent on coal for power generation, 0.5% is really a staggering number. A 0.5% loss for a 2,400 megawatt power plant would equate to 60,000 tons of coal being lost. That's over $1 million. Let's consider fertilizer, where some components are more prone to dusting than others. The loss of these components by excessive dusting can reduce the efficacy of the fertilizer dramatically. Dust suppression coatings are frequently used to keep all the components of the fertilizer together in the right ratios.
Now that we've identified the major challenges imposed by dust on industry, let's discuss the 2 main methods of dust control: dust collection and dust suppression. Dust collection is the most prevalent form of dust control in today's industrial world because it doesn't add moisture or chemicals to the process that generates the dust. That's the biggest advantage of dust collection. But dust suppression is growing in many industries and processes because it can either supplement dust collection or improve overall control, or it can replace dust collection entirely, often at a lower cost. Dust collectors may be single unit designs or a collection of devices used to separate particulate matter from the process air. They come in a wide variety of sizes and designs, from small units made for small workshops to large units that can measure hundreds of feet long and several stories high. Dust collectors are often used to recover valuable granular solid or powder from a process stream, and they can be employed to remove granular solid pollutants from exhaust gases prior to venting to the atmosphere. There are many applications of dust collection where they are the best available technology, and dust suppression is simply not feasible. Dust collection systems rely on 4 main components in order to effectively capture and collect the dust. The first are the exhaust hoods. These capture dust emissions at their source. There is virtually no limit to the number of hoods the system can support, but these hoods must be placed in close proximity to the process that generates the dust, and space is often limited. In some processes, though, ventilation is required to remove heat or fumes, so the addition of dust collection to those processes is less invasive. Still, many processes that would not otherwise require ventilation suffer from the noise created by the exhaust hoods. Exhaust hoods can also have the unintended consequence of removing more than just the target dust. Second is a system of ducts that transports the captured dust to the dust collector. If designed correctly, ductwork can be non-invasive and highly efficient. However, ductwork is often given very little attention during the design and installation phase, making it cumbersome to an operation when it's not well integrated into the equipment and infrastructure. Third is the dust collector unit itself, where dust is removed from the air and collected for disposal or for transport to another part of the process. Dust collector units are often large, bulky designs, and they are typically located outside of the building. The dust collected by these units poses many challenges. Some designs simply unload the dust into barrels, dumpsters, or other disposal containers, but many designs transport the collected dust back to the process stream, often depositing the dust into the process in a manner that requires the same collected dust to become airborne again and need to be recollected again, and that cycle can continue over and over. And fourth is a fan or motor system that provides the required suction. These are very noisy units and often require routine maintenance and balancing. Attention has to be paid to the selection and implementation of all four of these main components, as poor performance of any single component will adversely affect the entire system. There's four different classes or different types of dust collectors, and the proper selection of the right type of dust collector depends largely on the intended purpose. So let's talk about the four main classes of dust collectors. First, we have the inertial separators. These use settling chambers, baffle chambers, or centrifugal collectors to remove slower moving dust from the faster moving airflow. Think Dyson on a really large scale. Second, you have fabric filter collectors. These employ bags, cages, and venturi assemblies to remove dust from the airstream through mechanical filtration. The efficacy of these units is largely dependent on the filter medium, which can be modified to only capture large dust particles or modified to capture extremely small dust particles, such as the case with HEPA filtration. Third, you have wet scrubbers. These filter dust by impingement with water droplets. The smaller the droplet, the more efficient the scrubber. This is due to the slipstream effect. As a water droplet moves through the air, it creates an airfoil around it. The larger the droplet, the stronger the airfoil. Smaller dust fines simply move around the droplet and avoid contact altogether. Chemicals can be added to these systems to improve performance by changing the ionic charge of the water droplet in a way that makes it attract the target dust like a magnet. And fourth are electrostatic precipitators. These work much in the same way by imparting a charge to the particulates in the airstream, and ESPs utilize oppositely charged precipitator zones to collect those particles.
While dust collection does improve the overall safety of a facility or process, there are inherent safety concerns due to the general concept of their design. It's no secret that dust collectors often explode. This makes sense if you think about it, because you're essentially gathering dust fines, transferring them with high volumes of air through ductwork into a gathering area. The U.S. Chemical Safety Board found that in all industries, dust collectors are the equipment most often involved with incidents. Grinders, silos, hoppers, and mixers are also involved in numerous incidents. Similarly, an article in the Journal of Loss Prevention and Process Industry reported that 40% of all dust explosions can be attributed to a dust collector.
Let's take a look at a typical progression of a dust collector explosion. Here's a typical setup with a dust collector positioned outside of an industrial plant. Combustible dusts are carried from exhaust hoods to the drop box and into the dust collector. Dust builds up inside of the ductwork and often leaks from the ductwork where it builds up on surrounding surfaces. This picture highlights how combustible dust builds up on a horizontal surface like beams, ledges, pipes, and equipment. A metal ember or an impact spark ignites dust inside the dust collector, causing an explosion that moves upstream to the drop box. The fireball and pressure wave continue upstream through the ductwork into the facility. As the fire spreads through the ductwork, it gains in intensity. Meanwhile, the initial explosion in the dust collector shook loose dust that had accumulated inside the plant. That falling dust meets with the fire traveling through the ductwork and triggers a second and much larger explosion. The secondary explosion is usually the one that causes the most property damage and human casualties. As combustible dust awareness has increased, dust collector technology has also improved a great deal. New dust collector designs include explosion mitigation devices that help control the direction of the energy away from people and property. However, existing dust collectors still present a hazard, and it's challenging and often impossible to retrofit existing dust collector systems with these new explosion mitigation devices. Chemical dust suppression programs can be implemented to supplement or replace older dust collection systems that are at risk of explosion. In fact, 10 years ago, MinTech began incorporating our proprietary flame freeze additive into our dust suppression formulations to better protect against fires and explosions caused by combustible dusts. When the correct dust collector design is chosen, and when that design is installed properly and maintained properly, dust collectors can be very effective. Customer testing for dust collector effectiveness ranges from 30 to 90%, with the average falling right around 70%. Dust collector manufacturers typically promote dust collector efficacy of 95% or greater, but these are often based on insufficient data or in-house data that has not been audited by a third party. Of the few field case studies that are available for review, the average dust removal effectiveness averages around 80%. So in general, dust collectors are relatively effective.
Wes says in general because there's simply not a universally accepted standard for measuring the effectiveness of industrial dust collector systems. The most common rating or standard is ASHRAE's MERV rating. These ratings were established for general industry ventilation cleaning, but not industrial dust collector industry. Leaders in dust collection industry, ASHRAE, ANSI, and ISO have been working together to address the issue for more than a decade. And last year, they published Standard 199, which was developed for pulse clean dust collectors. Standard 199 only creates a uniform test for dust collectors. It requires a uniform report template as well. Summary data reflects performance factors that truly matter to plant engineers and operators. Standard 199 will be more widely utilized as awareness increases and customers demand their suppliers address the new standard.
Let's recap the pros and cons of dust collection before moving on to dust suppression. First, the pros. There is a wide array of design options for all types of dust and process conditions. Unlike suppression, collectors can separate fines by size and charge, and collectors don't add moisture or chemicals to the processed material. They can also play a dual role by providing needed heat removal or fume removal from a process. Another pro is that dust collectors are generally very effective, and models are available that are capable of HEPA quality filtration down to 0.5 micron or less. And NFPA compliant models are also available that more safely handle combustible dust, whereas no NFPA standard currently exists for dust suppression systems. And now the cons. Dust collectors are engineering intensive and have a lengthy design and installation process. Dust collectors are also relatively expensive with higher initial costs and higher ongoing energy costs. They are large and they are difficult to retrofit into existing processes. They require routine service and maintenance that often is not supplied by the manufacturer. And if a process is changed, the dust collection system often needs to be redesigned and repositioned in order to accommodate the change. Most units in operation today that are handling combustible dust are not NFPA compliant and have not been updated for safe handling of combustible dusts. And finally, dust that are collected then have to be handled or disposed of, and this often presents further safety or financial challenges.
Now let's turn our attention to dust suppression. Like dust collection, dust suppression has many pros and cons. Understanding them will help you select the right method of dust control for your operation. Dust suppression is defined as the application of water, surfactants, oil, or other chemicals in a manner that either prevents the dust fines from becoming airborne or mitigates fines that have already become airborne. The former is a proactive approach that binds, wets, or encapsulates dust fines to the substrate before they become airborne. This is often referred to as surface wetting. This video shows a coal conveyor being sprayed with a foaming dust suppressant in a proactive manner to prevent fines from becoming airborne. When dust suppression is applied after the dust has become airborne, this is a reactive approach, often called air wetting. Large open processes present unique challenges that the proactive approach cannot solve because the dust generation points are large and mobile. Another reactive example is a large dumping or loading operation, such as a truck dump or a barge loading application. In these conditions, a curtain of droplets is the best method for capturing and containing the dust fines.
In a proactive approach, foam can be used to provide chemical wetting of dust fines and physical encapsulation of the substrate, shielding it from air currents that may dislodge dust fines. Here's a typical schematic of a dust foam system. To make a dust controlling foam, you need three basic elements: water, chemical, and air. The goal here is simply to reduce the amount of moisture needed to treat a high volume or a high surface area. These types of systems are excellent for treating limestone, gypsum, coal, iron ore, and other material streams that are sensitive to moisture addition. A typical foam system will have a control panel connected to the process through relays, sensors, or PLC logic. This turns the system on and off and up and down based on the process activity. When activated, the water, the chemical, and the air all mix together in the system to produce a low moisture, highly expansive foam. That foam is then dispersed through hoses and nozzles onto the material at the desired point or points in the process. As little as 1 ounce of chemistry, represented by the shot glass, when mixed with a few gallons of water, can be expanded into over 100 gallons of foam capable of treating several tons of material. One of the main benefits of foam is that the addition of moisture and chemical is minimized to concentrations as low as 0.5% by weight of moisture and 1/1000th of a percent by weight of chemical.
Here's a simple animation that demonstrates how foam can provide better results than water alone. Let's start with a conventional water spray system. As dust escapes from a process, water is applied in small droplets, and hopefully the water and dust will collide. But there are holes in this plan, and dust can avoid capture and containment rather easily. With foam, you can have the same effect with far less moisture. Let's cut the moisture in half. We're then going to add a small concentration of chemistry and expand the mixture into a foam. There are far fewer holes for dust to escape through. We treated the same volume of area with less water, all while improving the dust control significantly.
A spray system is similar to a foam system, but just doesn't have the air component. The system shown here is a water and chemical spray system. Various chemicals can be added to the water depending on the material, the process, and the desired result. For example, coal has a negative charge, and it's hydrophobic, coal dust repels water. MinTech engineers utilize cationic additives to create a positive charge, therefore attracting the coal fine and allowing the water to wet faster with less water usage. Another example is when treating fertilizer. Some fertilizers can be treated with low volumes of moisture without compromising the fertilizer quality, but many require the use of oils, waxes, glycerols, and other non-aqueous solutions. So water is minimized or eliminated from the process altogether. These oils, waxes, and glycerols can provide additional performance attributes such as time-release coatings, nutrient enhancement, and other benefits to the finished product. The configurations, chemistries, and variations are pretty much endless, making spray-type dust suppression an extremely versatile method of dust control.
Here's a demonstration to help explain the benefits of low concentrations of chemistry on the wetting and encapsulation of dust fines. Both these beakers contain water. It's important to understand that water alone is actually not very wet. Watch as 1 gram of coal dust fines are added to the beaker of water on the left. The surface tension of the water is so high and the hydrophobic nature of coal is so strong that the coal fines will actually float on top of the water. We'll let it float there for a moment to demonstrate the strength of the opposing materials. We'll now add a few drops of chemistry to the beaker on the right. This represents a 1 to 400 dilution rate. When a gram of the same coal fines is added to the beaker, the chemistry has lowered the surface tension of the water while also changing the ionic charge so that it attracts the oppositely charged dust fines, and the difference is dramatic. Now to show that this experiment is not doctored, we will add the same chemistry to the other beaker of water. Watch how quickly the surface tension drops and the fines are pulled like a magnet into solution. These results are easy to see in a beaker, but the same effect occurs in surface wetting applications and air wetting applications. Extremely low concentrations of the right chemistry can provide tremendous improvements in performance, often reducing the amount of water required by 90% or more, and eliminating application points by 95% or more.
Let's expand on those concepts of water reduction and the elimination of application points, because that's one of the major benefits of dust suppression compared to dust collection. In many industrial processes, single point application can suppress dust through an entire process. This reduces the footprint of the system, reduces complexity, saves money, and improves overall quality. In this design, a dust suppression system is installed at the first transfer point. There may be dozens or more transfer stations downstream. If the right chemical is applied in the right manner, a single application point will prevent dust throughout the entire process. This is often called full-body dust suppression because the idea is to treat all sides of the material. That can be more challenging, though, than it sounds, because often the total surface area of all of the material can measure in the acres per ton. In systems that are processing many tons per minute, a full-body system is effectively treating many acres every few seconds. The trick is applying suppression chemistry to all sides of the material as it's being transferred. The first point is a topical application at the transfer header. The second point is from underneath and behind the falling ribbon of material. The third point is at the contact point where the falling material impacts the next conveyor. And the final point is a topical application that protects the ribbon of material for the remainder of its journey. This method incorporates the dust suppression chemistry onto all exposed surfaces, and this can be performed by adding a minimal amount of water and chemistry. When water can't be used, oils, waxes, and glycerols can be applied in the same manner. In some processes, such as blending, crushing, or shredding, the action of the process itself can be sufficient for coating all exposed surfaces with dust suppression treatment. Here's a diagram showing how a single application point at the first transfer can provide dust suppression through many downstream processes.
MinTech has performed numerous case studies to document dust suppression performance for our customers. In a study featured here, a coal-fired power plant was having problems with fugitive dust emissions during unloading and stack-out processes. Dust monitoring data showed an average dust reading above 7.0 milligrams per cubic meter. The plant was located near a marina, so dust would leave the property and end up on boats docked in the nearby marina, and the marina demanded a solution. There was already a water-only spray system at the rail unloader, but it was completely ineffective. Dust clouds would move through the water spray like it wasn't even there. It took less than a month from concept and design to installation and operation of MinTech's dust suppression system. MinTech replaced the nozzles on the existing spray system to achieve smaller droplet sizes while reducing water consumption by 70%. MinTech installed a chemical feed system that dosed Cultural 65 at a rate of 1 to 400 parts of water into the water flow. Cultural 65 was able to lower the surface tension of the water droplets, improve the wetting of the fines, and provide long-term binding properties that provided a dust control residual of 30 days. Notice the difference. The photo on top shows stack out when dust suppression is turned off. The photo at the bottom shows stack out when a dust suppression system is turned on. The opacity also dropped from 50% to well under 5%. Dust monitors show the results best. The average dust levels when the MinTech system was running were only 0.256 milligrams per cubic meter. That's a 96% reduction in fugitive dust emissions.
We've talked about three main types of dust suppression: water-only sprays, water and chemical sprays, and foam, which is made from water, chemical, and air. Let's compare them all side by side. Water-only spray systems add a lot of moisture. Even so-called fog systems or dry fog systems, they add a lot of moisture too. Typical application rates range from 2 to 5 gallons of water per ton of product processed. When chemicals are added to water spray systems, the amount of moisture added is reduced by half or more, and typical application rates drop to only 1 or 2 gallons of water per ton. Foam systems add the least amount of moisture, with rates as low as half a gallon per ton and sometimes even less. Water-only spray systems provide no physical barrier, only weak hydrogen bonding, whereas chemical water spray systems provide a slight physical barrier through ionic bonding. Foam provides the most robust physical barrier by layering many ionic films one on top of the other, eliminating dust emissions and protecting the substrate from wind. Water-only sprays provide the lowest coverage rate, while chemicals improve the coverage rate by double or more, and foams provide the highest coverage rates. Water-only sprays evaporate quickly. Most chemistries, though, reduce this evaporation rate significantly, and foams are extremely resistant to drying. Water-only sprays possess no ionic charge, so most dust will be repelled and evade contact by wetting of water droplets. Chemicals and foams, however, can both provide a cationic charge or an anionic charge, creating an attraction between the dust and the water droplets. Water provides the shortest duration of dust fine control, but chemical sprays and foams can extend the duration of dust fine control a great deal, especially when the right chemistries are employed in full body application. So to conclude, in processes and applications where foam dust suppression is possible, it can be the most cost-effective solution for dust control compared to the other two dust suppression methods. Now to recap the pros and cons of dust suppression. With proactive type dust suppression programs, dust never becomes airborne. It stays with the bulk material, reducing the need for cleaning, reducing the risk of combustible dust explosions, reducing downtime, and improving efficiency. If dust has already become airborne, reactive type dust suppression programs exist to improve dust suppression performance via air wetting techniques that minimize moisture addition and improve performance. Another pro, is that dust suppression programs have relatively low upfront costs and lower ongoing energy costs than dust collection. Plus, a single application point can be sufficient for multiple downstream process points. And service is included by the dust suppression system manufacturer, or at least it is for MinTech systems. Dust suppression systems have a smaller physical footprint and are easier to retrofit into existing processes. MinTech systems can be built on-site in virtually any size space available, or we're now building more and more systems off-site inside of enclosures that can be delivered ready to plug in and go. Dust suppression is simpler engineering than dust collection, and the design, fabricate, install, operate timeline is significantly shorter, a few weeks compared to a few months. There are a wide array of chemical options, like water-based, waterless, cationic, anionic, etc., for all types of dust and process conditions. Highly effective programs can achieve greater than 99% reduction in airborne dusts. And now the cons. Water and/or chemicals can be damaging to certain materials and process equipment. Water-only programs can use a high volume of water, which is challenging in some areas. Waterless dust suppression chemistries do exist, but they can be a lot more costly. Water-only programs and some chemical programs receive no service from the manufacturer of the system. MinTech is a little different in that regard, as we provide full service for free with the purchase of our products and programs. And finally, chemical-based programs require storage and handling considerations. While most chemicals used in dust suppression are pretty benign, there still needs to be considerations for product storage, handling, spill response, etc.
Let's compare the total cost of ownership now between these two system types. The dark blue area refers to a dust collection system, and the lighter blue is a dust suppression system. The following information was given to us by a coal-fired power plant that processes nearly 15 million tons of coal per year. This power plant has 4 units, and in 2003 installed 12 new dust collection systems at $1 million each through a capital investment project. The operating costs were higher than expected, and in 2015, this power plant ended up removing the dust collectors entirely and transitioned to a chemical-only dust suppression program. The initial investment for the new dust suppression system was only $500,000, purchased through the power plant's operational budget. So how would the total cost of ownership for these two systems pan out if they had been installed at the same time? For a dust collector system, we'll give it the best case scenario, which is operating costs, in this example, are $200,000 a year. This is a pretty conservative estimate. And for the dust suppression system, we'll give it the worst case scenario, which is chemical costs will rise 3% in price each year indefinitely. There is an obvious difference in the initial capital investment of a project at year 0. A dust suppression system can save this power plant nearly $11.5 million up front. Even if you pan it out to 10 years, a dust suppression system will run about $10 million less overall than a dust collection system. What if we back out even further to 20 years? You've closed the price gap some, but even at 20 years, this power plant could have saved nearly $7 million. In fact, it would take nearly 67 years for the cost of the dust suppression program to catch up to the high initial cost of the dust collection system.
We're going to open the floor for questions in just a moment, but let's quickly review what we've covered, at least the main takeaways. Dust collection has a higher initial cost, but can have lower ongoing costs if systems are maintained properly. Dust suppression has a lower total cost of ownership, especially in the first 10 years, where it's approximately 1/3 the cost of collection. Service and maintenance is intensive for dust collectors, whereas dust suppression programs offered by MinTech are hands-free to the customer. MinTech performs the installation, operation, and service of the system for life. Recent modifications to dust collectors have improved the safety profile of the dust collectors a great deal, but dust suppression has a better track record for safety, especially when the most current chemical technologies are employed. Dust collectors lack a widely accepted standard for efficacy testing, but they are good in general at greater than 80% dust control. MinTech dust suppression systems typically achieve 95% or greater dust control. Dust collectors are relatively large and cumbersome, while dust suppression has a smaller footprint, making them easier to retrofit into existing processes. The reliability of dust collectors varies greatly based on the manufacturer, the amount of service performed on the system, and other factors. The reliability of dust suppression systems serviced by MinTech is excellent. Our engineers and field technicians inspect and maintain systems on a routine basis, and they're on call 24/7 for emergencies. And finally, the implementation schedule for collection is much longer due to the level of engineering complexity involved. Dust collectors can take many months to design, fabricate, and install, whereas suppression has a much shorter startup of only a few weeks. That concludes our presentation. We're going to ask Kendra now if any questions have been submitted. Kendra?
Thanks, Wes and Chris. That was a really informative presentation, so thank you guys for putting that together and sharing it with everybody. We did get 3 questions so far from our audience, so I'll throw those out there for you and Chris to answer. The first one is it common for insurance companies to raise premiums based on dust generation processes? This just happened at our facility.
Well, it didn't used to be, but it is becoming a little bit more common, especially in facilities that handle or generate combustible dusts. In fact, MinTech, I think, has installed 3 or 4 systems in the past year or two where the cost of the system was offset by the reduction in insurance premiums.
Okay. And the second question is, my facility is in the process of installing a dust suppression system already, but are there any solutions available for removing dust that's been accumulating for years?
Chris, you want to get this one?
Yeah, sure thing. MinTech can perform a free site survey, and from that site survey, we can design a turnkey cleaning program just for you. Our low moisture foam dust encapsulation products will safely remove years of dust buildup from walls, beams, equipment, any other surface without requiring the plant to be shut down.
Okay. I have another question here. What type of water is required for the suppression/foam system? And they give some examples of, does it have to be city or river or well water?
We've worked with all types of water. A lot of our systems are set up, in very remote places where we're using well water or we're using processed water. We've used brackish water. Our chemistries can actually be tailored to the specific water on site. So we can add softeners when necessary or other additives to allow foam to be produced and stable, or to make our surfactants work properly, regardless of the type of water.
Okay. I have another question that's come in. So what is the difference between different Coltrol products? In one of the case studies, you mentioned Coltrol 65. So they're wondering what the different types of Coltrol products we have are.
Well, several are designed to be foamed, and while a lot of them are also not designed to be foamed. So the ones that are designed to be foamed have, they of course have additives in there to create a rich, thick foam that's low moisture. The type that are designed to not foam, they use wetting agents and penetrants and things of that nature. And then both types, foaming and non-foaming, we can add various types of binders. So some will use latex type binders, some can use lignin type binders. There's a variety that we can use. And then we also now are making a lot of our Coltrol products with our flame freeze additive built in, so that not only do you get dust suppression,
but you're also getting spontaneous combustion inhibition to prevent fires in coal piles or fires in silos. Anything that's been treated for dust also now has been treated to prevent it from burning. And I'm going to go ahead and anticipate the next question might be, well, if we're treating coal or something like that, we want to burn it eventually to get energy out of it. Will it have any effect on that? And the answer is no. We get that question a lot. We're putting the flame freeze on there to keep it from burning while it's in storage. But once it's crushed and blown into the furnace, there's no side effect. There's nothing that we're adding to it that's capable of keeping it from burning in those conditions.
Okay. I think we have time for just one more question, which is how can I support the implementation of Standard 199 for dust collectors?
In order to support the 199 standard, you can ask your dust collector supplier about the emissions performance, energy consumption, and the filter life of the dust collector. These are the three main underlying criteria covered by Standard 199 because they impact the total cost of ownership.
Okay. And we did have a couple questions that we weren't able to get to, but I just want to let the attendees know that submitted those. I've got your name and I've got your question. So we'll be emailing you later to give you the answer to your questions. We just want to make sure we wrap up in time and get everything made that we want to throughout the presentation. So that's it for our questions. And then Wes, do you want to share just a little bit more about MinTech and what makes us unique in the industry?
Absolutely. Just want to recap real quickly what makes us different is three key elements. We not only make the chemistry, but we also design and fabricate and install the equipment and then provide the service and maintenance of that equipment. And it really takes all three of those things working together properly to get the desired result. And then we do monitoring also on systems that we put in to make sure that we're achieving the dust reduction levels that we've promised and that our customer needs to remain compliant. We also do free demonstrations, which is pretty unique. We'll provide mobile units and the chemistry and everything to set up at your plant or your process to prove that our systems and our chemistries can work in your environment and achieve your results without any risk to you. So if you're interested in getting a free demonstration, our contact information is listed right here on this slide. You can call us, email us, or visit us online and fill out the form on our website, mintech.com.
Okay, great. Thanks again, Wes and Chris, for a really great and informative presentation. And thank you to our audience for coming today and for participating and submitting your questions. Like I said, if we weren't able to get to your question, we'll definitely email you an answer. Just for your reference, you can download our MinTech brochure in the handout section of your GoToWebinar application. And as a reminder, the webinar has been recorded, so you'll receive a link to this tomorrow. And in that link, you're also going to get a 5-question survey. So if you would just take a minute to fill that out, we would greatly appreciate it. It will just help us make sure that we bring you guys valuable information in the future. And if you think of additional questions or if you need more information on anything we've discussed today or any of our other services, please feel free to contact us. You can contact us at the email address that you see on the screen, solutions@mintech.com, or the phone number 800-556-3967. Again, thank you and have a wonderful afternoon.